So, way back when, even though it hasn't been that terribly long, we talked about Newton's second law. And we said that in our last chapter that sum of the forces, or our net force, was going to equal mass times acceleration. But I told you that this was really a special case. That really what Newton said was that we were going to have an impulse was going to equal a change in momentum. Now we're going to be back to our vector type activity now, because our force is a vector and an impulse is defined as our force times our change in time, and our momentum is mass times our velocity. So we get that. Now we will have conservation of momentum. And we're working right now with linear momentum. Because what we're going to see in a real short time is that we will also have rotational momentum, and we'll get there as well. But we talked about this, and so this actually gave me my force was equal to, I could do mass times my change in velocity over my change in time, plus my velocity times my change in mass over my change in time. And most of the time, this is going to equal 0, because we're either going to be dealing with such a short thing, or we're going to be dealing with our rockets, and then that will be up there, or the change in mass is going to be minimal. So we most of the time we don't have this change in mass, and that gave us that's acceleration, so that gave us our special condition. So this is what we're working with right now. So let's look at impulse, for example. So let's do this. I've got a barrier, and I have a car that's coming into the barrier, or a truck, because I can draw trucks a little bit better. And the mass of my truck is going to be 4,500 kilograms. And it's going to be traveling at a velocity of 27 meters per second. And we're going to come up to this barrier, and we're going to smash into the barrier. We're going to have a collision, because momentum it's looking at collisions. We're going to have a collision, and we're going to do a lot of collision type problems. And it's going to, the change in time to go from 27 meters per second to 0 meters per second is going to be equal to 0.001 seconds. So if I'm hitting the barrier underneath a bridge, we want to know the force exerted. So I'm going to have my force times my change in time is going to equal my change in momentum. So this will be the mass times velocity initial, velocity final minus velocity initial, is going to equal my force divided by my change, or times my change in time. The force that's applied is going to be the mass divided by the change in time. And we've got our velocity final minus our velocity initial. And so now we're going to get 4,500 divided by 0.001. and our velocity final is 0, and our velocity initial was 27 meters per second. The negative is going to be the force of the wall on our vehicle, so that's giving our direction. But if I do my 4,500 divided by my 0.001 times 27, I'm going to get 121,500,500 newtons. I.e., you'd be dead. Okay? So what does our seatbelt do? And we know now if I'm out on the interstate, the odds are I'm not crashing directly into a barrier. I'm now dealing with something that looks like this. We have these things that are in front of our barriers. So we're going to use the same starting condition, but what this does is this extends the time. And now my time to my collision is going to be, let's say it's going to be now 0.3 seconds that it takes as I come in to crash. Now, those of us that are in that crash probably can't tell the difference between the 0.1 second or the 0.3 seconds, but let's say that that happens. Now we're going to have our 4,500 divided by my 0.3 seconds. I still have my negative 27 meters per second. And now my force that's being applied
Can you move it down a little bit?
Sure. Is now 400 newtons. So just by extending the time, we're going to compare to what we had before. This is likely survivable. This is definitely not. So that's why they put those safety devices in out on the interstate. And we have lots of other things that are in our car to extend this time. We've got the crumple zones in the car. We've got our seat belts. We have a lot of those things that are helping us so that we're not just slamming into the barrier at this short the time. So it's not the fall that kills you, it's the sudden impact at the bottom that's going to kill you. So that's why we actually do those things when we're looking at our impulse. So let's start thinking about collisions. So if I have a marble and it's going to hit another marble, this marble is coming in with a velocity and it has a mass. This one is going to be sitting at rest. If this is a perfect collision, or we call it an inelastic or an elastic collision, sorry, an elastic collision, what's going to happen is our first ball will stop. And our first ball will have an equal to 0. And if these are both the same mass, so both of these have the same mass, this one is going to go off with the velocity of the first one. And we've played with that. We've played with marbles all the time. And this comes from our idea of conservation of momentum. Now, we can also, even in any collision, we're going to have conservation of momentum. And we're going to have conservation of energy. But we do get a special case for elastic collisions. For elastic collisions, we get conservation of kinetic energy. And that's how we can tell we have an elastic collision, is because we can get that conservation of kinetic energy. So for any collision, we're going to get conservation of momentum. We're going to get conservation of energy, but the special case for elastic collisions is conservation of kinetic energy. And that's how we will actually tell what kind of a collision that we have. Now we also have two other types of collisions. One we're just going to call real collisions. And the other is completely inelastic. Now, a completely inelastic collision would look like this. I got my bullet and I've got a target. And after the collision, the bullet is part of the target. They actually come together and they stick together. Real collisions are somewhere in between our perfectly elastic collisions and our perfectly inelastic collisions. So let's play with this one. So let's do this one. We're gonna play with a collision here. So I'm gonna have a steely. If we've played marbles, so this is gonna be a steely. It's gonna have a mass of 0.30. We'll do this 0.030 kilograms. It's going to come in and it's going to hit another marble. Okay, it's going to hit another marble. And this marble is going to have a mass of 0.02 kilograms. It's going to have an initial velocity of 0. This one's going to come in with a velocity of 3 meters per second. So this is the before. We're going to have an elastic collision. And afterwards, our steely here is going to have a velocity of, we're going to say 0.5 meters per second. We want to know the new velocity of this one. So when we do this, we know that the momentum before equals the momentum after. Now, you can use subscripts for these to help keep track. So this is going to be the mass of the steely, the velocity of the steely before, plus the mass of the other one, and the velocity of our other one has got to equal the mass of the steely, velocity of the steely after, and this is going to be before, plus the mass of the other one, the velocity after. And that's what we're trying to find. So we're going to solve for that first. Well, this is going to be easy because we started with 0. So I'm going to get rid of that because that's going to simplify my life. So I'm going to get mass of the velocity there minus the mass of the steely, velocity of the steely after, all divided by the mass of my first one, is going to equal the velocity after. So let's go ahead and do that. So I'm going to get my 0.03 kilograms. I started at 3 meters per second minus my 0.5 meters per second divided by my 0.02 kilograms. Okay, times 2.5. And I'm going to get 3.75 meters per second is going to be the velocity of this one going after. Now that would make sense because my Steely had a bigger mass than this one. So this one is going to take off at a faster rate. So this is another case where you've got to use this and you're going to come up with your own equations. So now we're going to do an inelastic collision. And this is why you're always going to lose with the train. And you get your trivia question for the day. So I've got my train engine. And we're going to put a big cow catcher on the front. So I got my Dr. Seussian type train. And there we go. And I'm going to give it a smokestack. And then I've got a poor little smart car sitting on the train track here. This is going to be coming in at 60 miles an hour, which is going to be 27 meters per second. This is a train, so it's going to have, this would be a very light train. So we're going to use 150,000 kilograms for my train. And this is the before situation. We're going to be nice to the poor little car. The poor little car, the after is going to look something like this. We got our train here, our Dr. Seussian train. And my little smart car, it's going to be nicely picked up on my train. And this is a inelastic collision. We want to know the velocity after. Okay. Or we can do the horrible thing and say, what is the fuel source for the train? I've actually given you all the information that you need for the fuel source of the train. Because if this is a classic steam engine, the shape of the exhaust pipe will tell you what its fuel source is. And if you've ever seen the picture of Golden Spike, you'll see that some of the trains will have, one train will have a thing that looks like this, and one train will have a smokestack that looks like this. This has a spark arrestor on it, so it's wood fired. That one is a coal fired. And it was just how you would prevent having wildfires with your steam engine going down the road. So there's your trivia question for today. So we've got a perfectly inelastic collision. We're going to do our momentum before. Oh, I got to give you the mass of the car. The mass of the car is going to be 3,000 kilograms. So the momentum before has to equal the momentum after. So this is going to be the mass of the train, velocity of the train. This has got an initial velocity of 0. And then we're going to have the mass of the train, velocity of the train after, plus the mass of the car, velocity of the car after. But after, the velocity of the train equals the velocity of the car. So that's our velocity after, because it is a collision. So now I'm going to get the mass of the train, velocity of the train divided by the mass of the train plus the mass of the car is going to equal my velocity after. So I'm going to get my 15,000 kilograms times my 27 meters per second. And it's going to be 153,000 kilograms on the bottom. And my velocity after is 26.5 meters per second. Now, if you've got a big, huge train, that mass is very small compared to my big, huge train, or you're going to lose the battle with the train every time. You're going to lose that train battle every time. Okay. Let's do a two-dimensional one. Okay, so I've got a car coming into an intersection. It's going to have a mass of, we're going to make it 6,000 kilograms. It's going to have a velocity of 15 meters per second. We've got another car coming into the intersection. Its mass is going to be 7,500 kilograms. And its velocity is going to be, we'll give it 20 meters per second. It's going to hit, and these two are going to attach together, and it's going to be a completely inelastic collision. And it's going to go off in this direction, and we want to find the velocity after. Now, like before, we have independent motion, okay? So we're going to end up with, and one of the things that we're going to want to find is this angle here. We're going to have the momentum before is got to equal the momentum after. So we can look at the x direction, and we can look at the y direction. Well, the x direction is going to be the momentum of our 6,000 car times its initial velocity. And the y direction is going to be the momentum of the 7,500 car and its initial velocity. And the momentum after is going to be the momentum, mass total, velocity, and there's my angle, and this is going to be x, so this will be cosine of the angle. And this will be mass total, velocity, sine of the angle. I now have two equations, two unknowns. So let's go ahead and calculate these. So my initial velocity in the x direction is 6,000 times 15. This is going to give me 90,000 kilograms meters per second. And I got my 7,500 times my 20. And I get 150,000 kilograms meters per second. Our mass total at the end is going to be 13,500 V cosine, and I get 13,500 V sine. Now I'm going to do a mathematical trick here, because sine divided by cosine is equal to the tangent of the angle. So I'm gonna go ahead and do my 13,500 V sine of my angle divided by 13,500 V cosine of my angle is gonna equal my 150,000 kilograms meters per second divided by my 90,000 kilograms meters per second. That cancels, that cancels, that cancels. This is equal to the tangent. So now I can do the angle is going to be the arc tangent. And that's going to be the arc tangent of 1.67. And that's going to say that that's 59 degrees. So now that I got my 59 degrees, we know what my angle is. Now I can just plug that back into one of these equations. So I'm going to do my 90,000 divided by my 13,500. Cosine of 59 degrees is going to equal the velocity. We'll do cosine of 59 first. And if I've plugged it into the calculator correctly, I'm going to have 12.9 meters per second would be the direction that it would be going off at, or the magnitude of my vector. So this is in 2 dimensions. Now the ballistic pendulum works like this. We've got our bullet that goes into the pendulum, and this is on a string. So once it goes in, we're going to get a conservation of energy to the top. And we're going to do this. We're going to measure the height. Let's say that the height is 1.5 meters. This is going to have a mass of, let's give it 1 kilogram. Our bullet has a mass of 0.1 kilograms. And we want to know the velocity of the bullet. So this part of the problem is a conservation of energy problem. This says that the kinetic energy at the bottom has to equal the potential energy at the top. Well, my potential energy at the top is going to be the mass of the block plus the mass of the bullet, gravity times height. So we can calculate that. So I'm going to have 1.1 kilograms, 9.81 meters per second squared. And my height is 1.5 meters. That's going to give me, I think that's giving me 16.2 joules. I'm going to recalculate that. I'm not 100% sure I did that right. Yep, I did. And that's going to equal 1/2 the mass times velocity squared. So we can find the velocity after is going to be 2 times 16.2 divided by my mass total, which is 1.1 kilograms. And that's the square root of that. And that says my velocity was 5.42 meters per second. So the momentum before is going to be the mass of the bullet, velocity of the bullet equals the mass total, velocity after. So the velocity of the bullet is going to equal the mass total divided by the mass of the bullet times my velocity after. So I'm going to have my 1.1 divided by my 0.1 times my 5.42 meters per second. And this says that it would be at 59.7 meters per second. So this is called the ballistic pendulum. Okay. I'm pretty sure brains are full. Questions?